guys, have your notes pulled up for 5-3 day 1, and we're going to be looking at first derivatives and second derivatives and what they can tell us about the graph of the original function named f. So before we get started, I came over here. You don't have to copy this down. This is just review, okay? Do you remember in chapter 4 when you were given a position function? And I was like, tell me when the particle was stopped. So you would take the derivative of the position function, and then you would set your derivative equal to 0. And then you would factor it, and you would get 1 or 2 times when your derivative was equal to 0, when your velocity was equal to 0. And then I would ask, okay, when is it moving right? When is it moving left? So what you all did is you made what I call a sign chart. And you drew like a number line, and you put the 2 times that you got when your velocity was equal to 0, you put them in your sign chart. And so I'm labeling this with velocity because we are looking at velocity right now. I know that my velocity was 0 at 1 second. How do I know that? Because I did it. I set it equal to 0. I found those 2 numbers. So my velocity was equal to 0 here and here. Now I wonder, leading up to 1 second, which way was it going? So what I would have you do is plug a number into the left of 1, like, 0. And I like plugging it into my factored version. If I plug in 0 to velocity, I get a negative times a negative, which is a positive. So I know that leading up to 1 second, my velocity was positive. The particle or whatever was traveling to the right. What about between 1 and 6? Pick a number, plug it in to your velocity. So like, 5. I'll plug in 5. And I like to plug it into my factored version. Ready? Plug in 5, that piece is negative. Plug in 5, that piece is positive. A negative times a positive is a negative. So from 1 to 6, whatever was the problem was about was moving to the left. And then from 6 on, so pick a number anywhere to the right of 6. You can pick any number, like 100. This is positive, this is positive. So we can say that the particle was moving to the right. Okay? That's just a review. That's how we worked with derivatives and velocity. So, kind of forget about velocity right now. Let's just focus on what a particular function might look like and what's happening with its derivatives. So, I can say that checking out this blue function, we got a lot going on this blue function. So it looks like this is the lowest point, so I can call it an absolute min. If I do my toothpick test on my function, I can see that my tangent line, my derivative, is positive. It's getting less, it's getting less. Right here, I can see that my derivative is 0, my slope is 0. Moving on, positive again. Notice that even though my derivative was 0, I did not have a peak or valley right here. When can a peak or valley occur? When your derivative is 0, or when your derivative blows up. However, just because your derivative is 0 is no guarantee of a peak or a valley. Keep that in mind. Okay, so slope is positive, derivative is positive. Slope is 0, derivative is 0. Slope is positive, derivative is positive. Slope is 0. Notice now we do have a peak. We have a local max. You know why? I went from a positive slope to a negative slope. The function was increasing, it leveled off, and now it's decreasing. Local max. Moving on. Negative slope, negative slope, negative slope, zero slope, positive, positive, positive. Local minimum. Why did a local minimum occur? Because my derivative, my slope of my tangent went from negative to zero to positive. That's when a local min occurs. Positive, positive, positive. Right here, confused tangent line. Derivative is undefined. However, when my derivative is undefined, that means my derivative blows up. We can still call this a critical value. And check out what happens at this critical value. I went from positive slope, increasing function, to negative slope, decreasing function. I have a local maximum right there. Local maximums can occur where your derivative blows up. No guarantee, but they can, because I went from a positive slope to a negative slope. Now, negative slope, zero slope. So critical value, more negative slope, negative slope. No local max, no local min. Why? Because it was negative slope, zero, negative slope, negative. Didn't switch slopes. For a local max to occur or a local min to occur, your derivative has to equal zero or blow up, and your slopes have to switch. My slope switched from negative to positive for a minimum. My slopes switched from a positive to a negative for a maximum. Has to happen. Let's try figuring out some local mins and maxes or absolute mins and maxes without a picture. Oh golly. Without a picture, and we are not looking at a cone of shame. We are looking at the overall function. So first thing I can tell right off the bat, this is a cubic function. We're not going to have any absolute extrema. We might have a peak and a valley, but no absolutes, because it's a cubic. Y'all know what a cubic, you know what the end behavior of a cubic looks like. So let's do our first derivative test. Let's see, does our derivative ever equal zero, or does it ever blow up? Here we go. Derivative. You know what those are? Those are critical values. Those are two x's that caused your derivative to be zero. Will your derivative ever blow up? No, it's a quadratic. Quadratics don't blow up, ever. So I got two critical values. There might be a peak and or a valley, at these two places. Let's find out by looking at a sign chart. So let's make a sign chart. I'm going to put -2 on my sign chart and +2 on my sign chart. And here's what I want to find out. All I know so far is that my slope is zero. So it could look like this slope of zero, or it could look like this slope of zero, or it could look like this slope of zero. I know it doesn't look like this because here my slope is undefined. So I've got maybe one of these situations going on. How do I know which situation's going on? Well, I need to look at the slope. I need to look at leading up to my critical value. What was my slope doing? leading away from my critical value, what was my slope doing? What was my slope doing? What was my derivative like? So, on my sign chart, I'm going to label it with f prime because we're looking at what f prime looks like at that location. So I know that f prime was 0 here and here. Let's look at numbers over here. And again, I'm going to use, it doesn't matter which version you use. I'll use 0, and I'll plug 0 in right here. Hold on. I knew something wasn't right. 0 is not over here. Silly me. How about negative 10? Let's put in negative 10 because 0 is here, not there. Okay, now that we've got that cleared up, let's put in like a number over here like negative 10. So negative 10 squared, that's 100. That's going to turn out to be positive. That's better. What's happening between these two critical values? Now I can use 0. Plug 0 in anywhere into your derivative, and I get a negative. Pick a number over here, like 10, plug in 10 to your derivative, and you get a positive. So here's what was happening on F. Since my slope was positive, F was increasing. Can you see how that has a positive slope? Since my slope was positive, leading up to this critical value, F was increasing. What was happening at this critical value? Slope was 0. What happens away from the critical value? So as I lead away from the critical value, my F prime, my slope is negative. Look what just happened right here. I have a local max. Positive slope, 0 slope, negative slope. Local max, right there. I'm going to write it down so we don't forget. Local max. Okay, then what? Negative slope, negative slope, negative slope until a critical value of 2. And at this critical value of 2, my slope was 0. So it's F was decreasing, slope of 0. Then what happens leading away? Positive, positive, positive. Ha-ha. Negative slope, 0 slope, positive slope means that F has a local minimum right there. Now, be careful. Negative 2 is not the maximum value. Negative 2 is where the maximum value occurs. We still don't have the actual value. And positive 2. Positive 2 isn't the minimum value. It's where the minimum occurs. We still have a little bit of work to do. I think it says, find the extreme values. Okay, it's asking for y's. All we have are x's so far. We need the y's. So let's find the y's. Let's do f of, and we're using our two critical values. Usually somebody asks me at this point, okay, hold on. Do I plug in my critical values into the original or the derivative? Well, when you plug negative 2 and positive 2 into your derivative, don't you get 0? We want to know what the y values on the original function are. So if I plug in negative 2, I get 11. And I plug in positive 2, I get negative 21. So 11 is a local maximum value. Negative 21 is a local minimum value. All right, let's do a harder problem. This one involves a quadratic times e to the x. Let's work on its derivative. And it looks like we're going to have to do product rule. So I'm going to go 1 d2, love that derivative, plus 2 d1. We need to determine, does this function, which none of us know what this looks like, does this function ever equal 0 or does it ever blow up? So I think what I'm going to do here, we do not know what is going on here, but both terms have an e to the x. So I'm going to pull out an e to the x, and here's what I have left. I have an x squared and a 2x and a minus 3. So this is g prime. Now here's what we have to ask ourselves. 2 questions. Will this ever be 0? I think so. We can find out where. Will this ever blow up? The answer is no. You know how I know? This is a quadratic, never blows up. This is an exponential function. You know what the graph looks like. It never blows up. This never blows up, this never blows up, means g prime never blows up. All we have to do now is let's work for where does it equal 0. So my quadratic factors, like that maybe, positive 3, negative 1, yes, yes. So I've got 3 things multiplied together to equal 0. Either this quantity is 0, x equals 1, or this quantity is 0, x equals negative 3. Let me write those down. You with me? Either this quantity is 0, x would have to be 1, or this quantity is 0, x would have to be negative 3, or this quantity is 0. Is e to the x ever equal to 0? No. If you look at the graph of e to the x, y never has a value of 0. It never touches the x-axis. So e to the x never equals 0. So the only 2 x's that are my critical values that cause my derivative to be 0 are 1 and negative 3. All right, let's make a sign chart. Here's my sign chart. I'm labeling it with G prime because G prime is what we're looking at. G prime shows us the slopes of G. So we're looking at G prime. We took our critical values, putting them in a sign chart. Here we go. Ready? All right. Pick a number over here. Plug it in G prime. So how about like negative 10? It doesn't matter what I plug in to this. By the way, let me just draw that really quickly so you know what I'm talking about. Like I'm thinking that all of you are picturing this graph as I'm talking, and I should not assume that. So here's what the graph of e to the x looks like. No matter what x is, this will never attain a value of 0. Also, no matter what x is, a negative or 0 or a positive, no matter what x is, the result is always a positive y value. So, ready? Let's take negative 10 and plug it in. Take negative 10, plug it in. This is positive all the time. This is negative. This is negative. So G prime is positive back here. Pick a number in here somewhere, maybe 0. Ready? Plug in 0. That's always positive. A 0 makes this positive, and a 0 makes this negative. Positive, positive, negative, negative. Pick something over here like 10. Positive, positive, positive. Remember, at 1, slope is 0. At negative 3, slope is 0. Here's what's happening on G. You ready? The slope of G is positive here, which means G has a positive slope. G is increasing. Slope of 0. Negative slope. Oh my gosh, local max right there. It went from positive slope to 0 to negative slope. Local max right there. Local max right there. And then during this range right here, we've got a negative slope. Negative slope, negative slope, negative slope. Slope was 0. Positive, positive, positive. Local min right there. Local min right there. So let's take our two critical values, and we know that there's going to be a max when x is negative 3, a min when x is 1. Let's just go ahead and find those y values. And they're going to be yucky, but it's okay. What were they? Negative 3. 9 minus 3 is 6 times e to the negative 3. 6e to the negative 3, or I can say 6 over e cubed. Local maximum value. Now plug in 1. Where am I? Plug in 1. 1 minus 3, negative 2 e to the first. Local minimum. Okay, and then on the back is just a review of how to look at the first derivative to see maxes and mins. So when your derivative is 0, you can have a local max if your slope goes from positive to negative. When your derivative is undefined, you can have a local max if your slope goes from positive to negative. Remember, you check to see where's my derivative equal to 0, where does my derivative blows up, and then look to the left and to the right for the slopes. Okay? Local mins can happen when your derivative is 0 and your slope was negative and it switches to positive. That's a local minimum. A local min can also occur when your slope is undefined, when your derivative blows up, and you go from a negative slope to a positive slope. That is still a local minimum. But you know what? No mins and maxes have to occur. So here's an example. Here's an example of when your derivative equals 0. Okay. But look, you can have a positive slope, derivative is 0, and more positive slope. There is no local anything there. Another example, your derivative can be undefined. You can have a negative slope leading up to it and a negative slope leading away from it. There is not a local anything going on there.